To go up to the fourth floor, there is 2 elevators. So one is outside of that exit, and then another is just around after that, going out from that exit. Okay? Okay, thank you. So then next slide. Okay. So then here's the agenda. You also have this in your printout. So we're going to start from a company video and then a video message from our CEO, Paolo De Racca. Then video, please.
Hello everyone, and welcome to the Nora R&D Symposium here at the Italy Pavilion at Expo Osaka 2025. For more than 100 years, the Nora has contributed to the progress of electrochemistry, a science that plays a vital role in improving people's lives every day. Our journey has always been about research that goes beyond borders and brings together people, ideas, and technologies for a common goal. This is why we have a long history of organizing scientific symposiums in the very places where innovation happens, our R&D laboratories around the world. Today we are proud to continue this tradition here in Japan, a country that shares our passion for technology and excellence. Just like Expo brings people together from all over the world, our symposium is not just a meeting of scientists. It is a place of collaboration that breaks down barriers and creates connections across cultures and disciplines. This is the true spirit of innovation and the true spirit of Expo. For the past 100 years, we've been developing and producing our cutting-edge technologies, always focusing on our impact on the planet and on our communities. Today, more than ever, sustainability is the core of everything we do, and moreover, in how we do it. And as we look ahead, we promise to keep pushing the boundaries of research and to put our technologies at the service of a better future, whether in electrochemistry, the energy transition, or access to clean water. These are the challenges that unite us and the opportunities that inspire us. I want to express my heartfelt thanks to our Japanese team for making this event possible, to all of our researchers, speakers, and to all of you for joining us. Your presence here shows the strength of our shared commitment to innovation and sustainability. Thank you and enjoy the Nora Symposium.
In the history of every great company, there is a constant, a visionary idea. However, an idea alone is not enough. The key to success is the courage to turn that idea into reality, the determination to face the unknown, and to envision a different future. It's not the courage of heroes. It's the courage of those who know the value of their ideas and understand that they can make a difference and change the world together. Our history started exactly with that. A brilliant idea of a young student named Oronzio de Nora in Milan. 100 years later, de Nora, a global leader in electrochemistry, is committed to develop unconventional solutions for the energy transition to decarbonization, the green hydrogen economy, and clean water for everyone. But success is not a solitary act. It requires the collaboration of brilliant minds and passionate hearts. This is where you can come into play. Join us. Bring your talent, your passion, and your determination to de Nora. Inclusion, well-being, professional development, personal self-realization, and true sustainability are not just words, but pillars underpinning our vision. Leverage available talents as catalysts for a sustainable future. As every visionary idea, it will not come true alone. We need you.
Okay, so next agenda is company introduction from our CTO, Christine Urgege, please.
morning, good afternoon, also from my side. My name is Christian Ruggiega. I want to welcome you to the 14th Symposium of the Nora here at the Expo in Osaka. As anticipated by our CEO, we have now more than 100 years of history, and since 1923 we have been showing every day one purpose: to provide the most effective, efficient, and reliable technologically advanced solution for electrochemical, water, and energy transition. We have achieved this by listening carefully to our customer and the global society, and we keep improving and delivering our products to solve customer problems for a better tomorrow. We are the world's largest provider of coatings for all kinds of electrochemical technologies. We are as well a leader in the emerging sustainable technologies like the energy transition business, and we are a recognized provider of water treatment and wastewater treatment solution as far as disinfection and filtration. We are proud to be a listed company since 2022 on the Milano Stock Exchange. Here, I think in this slide, we can see very well how we connect people and we collaborate worldwide. This is the distribution of our revenue, people, laboratories, and operative companies. These are the figures of last year. We have been delivering almost 900 million of turnover, evenly dispersed between the three regions, APAC, EMEA, and Americas, in which we have more than 2,000 people, 2,100 I would say now, and 24 operating companies. We have been building on our heritage of more than 100 years of history, and let's say on a solid background of more than 3,000 patents collected in 278 patent families. And here you can see that also our team, it is very well spread evenly across all the region, including the R&D centers, which I'm proud to lead. We have 2 R&D centers here in Japan, 2 in the United States, and 1 in Europe, let me say, in Italy. Our purpose, mission, and vision. Our mission, it is to provide agility and green technology for value creation, and we do this by leveraging available talents as catalysts for a sustainable future. And in every day, we empower collaboration and champion resilience. In this slide, you can see a little bit of our timeline. 100 years are honestly quite a lot. In short, in the first 8 years of our history, we have been pioneering electrochemistry, including chloralkali technologies, electrocatalysis for electrogalvanic industry, electrometallurgy, and many other applications. One of our transformation happened in 2010, one of the biggest one, when we had acquired from Mitsui the remaining shares of Permelec Electrodes and Chlorine Engineers, one of the largest company manufacturing chloralkali plants worldwide. In 2015, we have conveyed this company to our joint venture partner, Nora, creating the so-called now ThyssenKrupp Nucera, which is one of the leaders in the chloralkali industry and hydrogen. In more or less in the same years, we started also our journey expanding in the water domain, acquiring from Severtrend Services the water purification and water treatment business, which has been, let's say, one of the most successful acquisitions we have done so far. A few years later, we started our journey in the energy transition, entering in what it is now called the hydrogen revolution. And also the company started changing their skin because the family, which so far had owned 100% of the company, has decided to introduce in the shareholding structure some minority investment from Blackstone, followed by Snam, and then, as I was saying before, to the listing. We have a comprehensive portfolio of mission-critical solutions for high value added and also aftermarket services. As I was saying, we have 3 main business units: electro technologies, energy transition, and water technologies. And there is no better words than this picture, I would say, to share with you where we're actually entering into, from the infrastructure, municipal, consumer life, mobility, communication, smart technologies, industry and chemicals, power and energy storage. What we do, we normally add value to our customer by enhancing the performances, by giving our product, increasing the quality of our product, and provide environmentally sustainable solution for the market. We also support our customer under the business continuity standpoint with remote monitoring and online support for their operation, with long-term supply and maintenance agreement, and we have tailored solution including energy service for the ones that are asking that. How we do that? Mainly with a close cooperation with our partner, with our customer. So, for instance, with the joint development agreement and other similar agreement. We make our services available also for rental, and we have flexible offers under the commercial and duration standpoint. Last but not least, sustainability has been in our DNA since ever. Here you can see some of the recent awards that we had achieved. But I wanted to say that we are contributing for more than 9 SDGs goals from the United Nations. We provide clean, sustainable, and innovative solutions while promoting a circular economy with engaged people who are eager to make the difference. The Nora, discover more. Thank you very much.
So thank you very much, Christian. So now the next speech is from Mr. Toshikazu Hayashida. He is talking about advanced industry through electrolysis, new technical journey. Hayashida-san, please.
Yes, good afternoon, everyone. I'm Toshikazu Hayashida. I'll be presenting our history and our technologies under the title of Advancing Industry Through Electrolysis. Let me briefly introduce contents of my presentation. Firstly, I'll explain our history and applicable field of our technologies. Then I'll go into the detail of our technologies. Finally, I'll conclude with our future outlook. Nora was established in 1969 when Japan reached the peak period of rapid economic growth. While chemical industry in Japan was undergoing unprecedented expansion, but pollution and labor issues were also beginning to emerge. Under the circumstance, Nora was established and has dedicated itself to contributing to industrial growth and clean global environment through our electrochemical technology. After the establishment in 1969, we have commercialized DSA electrode for chloralkali electrolysis. And subsequently, we also developed DSA electrode for oxygen generation. The application is such as copper foil production, metal electrowinning, and electroplating. And in 1999, we also developed activated cathode for chloralkali electrolysis. After becoming Nora Group in 2010 and establishment of Okayama Works in 2014, we expanded our business, not only electrodes, but also electrolyzers and the systems. As you can see, we can proudly say that we have grown together with electrolysis technology development and industrial growth. Let me introduce our core technology, DSA electrodes. This electrode is originally developed by Dr. Henry Baer. And this electrode consists of metal substrate with a mixture of noble metal oxide and valve metal oxide. And it was prepared by thermal decomposition process. This electrode has significantly low overvoltage, very high activity, so it has contributed to energy saving in many industries. And it also has good durability, low consumption, so it also contributed to reduce the maintenance frequency and operational costs reduction. In addition to that, this electrode is made of stable and environmental friendly materials, and it does not generate unwanted byproducts, so it also contributes to clean environment. The applicable field of DSA electrode is largely divided into 3 categories. One is chlorine generation. The field is chloralkali electrolysis and water purification and lithium recovery. The final products are papers or basic chemical compounds and drinking water and recycled lithium. Secondly, second field is oxygen generation. The industries are copper foil production and metal electrowinning and electroplating. Final products are metal products and metal electroplating products and printed circuit boards for computers and current collectors for lithium-ion batteries. Third category is hydrogen production. Hydrogen production is related to water electrolysis. And the unique one is the tritium concentration. I'll explain the detail in following slides. Firstly, I'll talk about chlorine generation. This is the simple illustration of chloralkali electrolysis. Chloralkali electrolysis is a sophisticated process because variable products are generated from both sides, anode side chlorine, cathode side hydrogen and caustic soda. It's very efficient process, but the problem is that oxygen is generated as a byproduct. In order to solve the problem, we have a wide lineup of DSA electrodes like this. These specifications have different chlorine selectivity. You may wonder why we have some different chlorine selectivity specification. Because at the first glance, it seems that high chlorine selectivity would be always better because chlorine is the desired product, final product. I will explain in the details. And this illustration is very simplified and exaggerated illustration, but in case of medium chlorine selectivity anode, oxygen is generated to some extent, but oxygen generation can consume hydroxide ion, which migrate from cathode side. In contrast, in case of very high chlorine selectivity anode, it generates chlorine selectively. So hydroxide ion from the cathode is not consumed by oxygen generation and react with chlorine and generate hypochlorite, and finally it becomes chlorate, which is very difficult to decompose. Decomposition of chlorate requires a lot of hydrochloric acid, so too many chlorate generation leads higher operating cost. So optimal anode specification varied, depends on the customer's plant and customer's request. So that's why we have different specification of DSA electrode. And this slide shows the why chlorine selectivity is different. And yes, chlorine and oxygen selectivity is determined by voltage difference of chlorine generation and oxygen generation. Basically, oxygen generation's Tafel slope is much higher than chlorine generation. So at the current density in industrial use, chlorine generation is dominant. And we can control the chlorine selectivity by changing the catalyst and bulk metal and preparation conditions. And sometimes chlorine generation activity and chlorine selectivity show the trade-off relationship. The reason why is that let's consider the same catalyst with different surface area. In case of in case of small surface area, it shows actual very high actual current density. So chlorine generation activity is low, but oxygen over voltage is too high, so chlorine selectivity is high. On the other hand, in case of large surface area anode, it showed very low over voltage because of very low actual current density. But oxygen over voltage also decreased, so selectivity will decrease. That's why sometimes oxygen and chlorine selectivity and chlorine generation activity showed trade-off relationship. Let's move on to next topic, reverse current absorber. Reverse current is a significant factor causing electrode deterioration. When operation is stopped, electrolyzer is shut down, reverse current flows through manifold and bipolar plate. It's this phenomenon is like batteries because after the electrolysis, active substances near the electrode. So charged battery, it's like charged battery will discharge when the circuit is formed. And especially in bipolar electrolyzer, large current flows at the middle of electrolyzer due to superimposed effect. So for center part, very severe conditions of electrodes, and it sometimes causes short life. So addressing reverse current issue is key to achieve long electrode life. We developed reverse current absorber. In case of no reverse current absorber, the potential will shift to the catalyst deterioration reactions. But if enough amount of reverse current absorber is introduced, the potential stays the redox reaction of the reverse current absorber and does not reach the catalyst deterioration reaction. So we can prevent catalyst deterioration by reverse current absorber. And let me introduce our system, which utilizes chlorine generation. It's called SECRO, which can produce hypochlorite on site. In some cases, hypochlorite solution is transported to water purification plants. In this case, it involves the risk of hypochlorite leakage during transportation and decomposition during storage. But with our SECRO, it can eliminate these issues because we can produce hypochlorite on site from water and salt. And we recently introduced SECRO in water purification plants in Hong Kong. I'd like to move to next topic, oxygen generation for copper foil electrowinning and electroplating. This illustration is copper foil process. Oxygen generations occurs on the anode side. On the other hand, copper foil is deposited on cathode drum and then wound up by this roller. In case of oxygen generation, interface deterioration can occur. because of the electrolyte penetrate into the interface and cause passivation. So although efficient amount of coating remains, cell voltage can increase. It's different from chlorine generation anode. In case of chlorine generation anode, the catalyst is consumed from the top and gradually decreased. So it's it can expect the life easily, but in case of oxygen generation, interface deterioration can also occur. So preventing interface deterioration is key to achieving long electrode life. So we developed interlayer technology and to prevent electrolyte-rich substrate. And interlayer technology can also show trade-off relationship between the coverage and conductivity. But we found that arc ion plating followed by heat treatment showed good coverage and good conductivity, which can prevent electrolyte penetration while keeping good conductivity. So implementation of interlayer technology has improved anode durability and extended the anode life significantly. This is another application in oxygen generation. It's electroplating, especially for printed circuit boards. In electroplating process, some additives are added into the electrolyte to obtain uniform film of electroplating, levelers and suppressors and brighteners. And these additives can be decomposed by anode reaction in case of normal DSA electrode. And it causes the issue of unevenness in electroplating, decrease the quality of electroplating films. So we developed the DT coating. DT coating is the top protective layer to prevent additives reaches the active surface of DSA coating. As a result, additives are not decomposed by anode reaction, and we can maintain the uniform electroplating film. So DT anode enables electroplating while preserving additives. Let's move on to the next topic, hydrogen production. This page shows our alkali water electrolysis system called Dragonfly. Our colleague, Alessandro-san, will present this Dragonfly in the detail later. So what I'd like to say is that the Nora provides now electrolyzers and systems in addition to electrodes. And let me introduce unique process utilize hydrogen generation. It's a tritium concentration process. Tritium concentration measurement is very important to check the safety of treated water from nuclear power plant. For the measurement, tritium needs to concentrate it due to the very low concentration. But in case of traditional method, oxygen and hydrogen are mixed, and it has a risk of detonating gas formation. In addition to that, this is not a zero-gap system, so for increasing the conductivity of water, alkali or something needs to be added for conductivity. It leads the process is very complicated and time-consuming. In contrast, our Tripura can solve these problems because hydrogen and oxygen generated separately thanks to the ion exchange membrane. And it's a zero-gap system with MEA, membrane electrode assembly. So no additives are needed for conductivity. As a result, our Tripura can make the process is very simple, and Tripura can enable safe and easy analysis of tritium concentration. And I'd like to explain our future outlook. The Nora will continue contributing industrial growth, development, and environmental sustainability through not only DSA electrodes, but also systems, complete electrolysis solution like Dragonfly, and MEAs, membrane electrode assemblies, like Tripura. Thank you very much for your kind attention.
Okay, thank you very much, Hayashida-san. So we have now Q&A session, so I can accept one or two comments or questions. Anyone likes to have some? Okay, so then, of course, we have time to discuss with Hayashida-san also in the party, so please take opportunity there. Okay, thank you very much once again. So now, next presentation is from Dr. Naoki Shida from Yokohama National University.
Thank you for the introduction, Yasui-san. And first, I'd like to I'd like to thank to the people in Nora and also Nora Permec, Japan, especially Kato-san for the kind introduction. I'm really, really happy to be here. I'm really honored. So today, I'm Naoki Shida from Yokohama National University, and today I'd like to talk about our effort, and I'd like to talk about the trends and outlook of the organic electrochemical technology for sustainable chemical manufacturing. Okay, right. So the topic today. So my topic of my presentation is not about the normal electrolysis, as you may know, like hydrogen evolution or CO2 reduction. I'm working on more on the organic chemistry side and using electrochemistry. And why we are working on organic electrosynthesis? As you may know, that chemical industry of course, chemical industry is essential for our lives. So, for example, we're using the pharmaceuticals and plastics, and everything in our lives is based on the chemical industry. So chemical industry is essential, but the problem is that chemical industry is consuming a lot of energy and emitting large amount of CO2. Actually, the amount of CO2 coming from this chemistry sector is at the 3rd position, and the chemistry sector is the largest energy consumer of all the industry. Sorry, the image is a bit blurred, but another challenge for the chemical industry, I would say, is the generation of the waste. So here's a famous metric for the generation of waste concomitant with the chemical production that is called E factor, which is defined, very simple equation that is defined as a ratio of the mass amount of waste generated from the production of the desired product. For example, if you think about the production of epoxide, ethylene oxide, if you take the route using the known as a chlorohydrin process, that is only up to 25%, because by using the chlorine as an oxidant, here you generate basically 2 other additional waste. On the other hand, if you use the oxygen, dioxygen as an oxidant, you basically use all the atoms to the desired product. So in that case, E factor is 100%. And E factor is very small for the large industry, like oil refining and bulk chemicals. But that could be a problem in the case of the fine chemical production and pharmaceuticals. And at the worst case, we are making almost like 100 times of the waste compared to the desired product. So we don't really know what we're producing in this case. So that could be another problem of the chemical industry. That's why we are trying to incorporate the electrochemical technology to make the chemical industry more sustainable. Why electrosynthesis is sustainable? Electrochemistry can, in electrochemistry, oxidation and reduction proceeds via electron transfer at the electrode, of course. And in that case, we can say that electrolyticity is a driving force and electrons are reagent. That is important. Electrons are reagent in this reaction, and which means that electrosynthesis is energy-saving, wasteless chemical process suitable for sustainability. So what we are thinking here is that we want to replace not everything, but some suitable thermal process to the electrochemical process driven by the renewable energy. So then we believe that we can make the chemical industry a bit more sustainable. So here's one very simple example. So this is, I'm showing this slide to show that electrosynthesis is not only the matter of the sustainability, that is also about the economics. So if you think about very simple organic chemistry reaction, alcohol oxidation, which makes aldehyde and carboxylic acid, both are very important for the chemical industry. And if you run this reaction, if you open the textbook, it says like you can use like this type of chemical oxidant. And the price I'm showing here is 1 molar, so 1 mole of the chemical oxidant. And probably equimolar or excessive amount of the chemical oxidants are required for this reaction. On the other hand, also another problem is that like these chemical oxidants generate equimolar amount of chemical waste. On the other hand, if you take electrochemistry as a reaction methodology, the 1 mole of the electrons, so 1 mole of electricity is less than 10 yen, so much cheaper compared to the chemical oxidants. So there should be economic benefit for like taking the electrochemical process for the chemical production. When I give a talk like this, like many people says, okay, electrosynthesis sounds very interesting, but like, does it scalable? And I want to say yes, and I'm pretty sure the audience in this floor already know about this, because there are so many electrochemical processes that is industrialized out there. For example, chloralkali process, of course, is large, and also the aluminum production is a huge industry. And adiponitrile process and toluene oxidation process are two most famous electrochemical organic synthetic process. I'm going to explain a bit deeper on these two processes. First one, the adiponitrile process, which was invented by Monsanto first, and then which was also run later by BASF, as well as the Asahi Chemical Company in Japan. In this process, acrylonitrile, the starting material, is reduced to make a dimer. So it's a reductive hydrodimerization reaction to make adiponitrile. And this reaction so this product is then transformed to adipic acid, which is a material for the nylon 6,6, so which is required. It's a very important industrial reaction. So in this process, the reaction is optimized, very uniquely optimized as an emulsion electrolysis process, as shown here. In the undivided cell configuration, in the water, the acrylonitrile is make an emulsion and run the electrolysis to afford the desired product as shown here. To make the surface area larger, of course, the bipolar electrochemical setup, so bipolar electrochemistry is used in the industrial scale. And I looked up the old literature, which is actually showing the efficiency of this reaction. So the data is like 1970 or 1980, so a bit old, but it says their specific energy consumption is 2.43 kilowatt per gram, which means about like 7.9 yen per mole, based on the assumption that like we are thinking the 30 yen kilowatt hour of the electricity price. So the value I'm showing here is like very similar to the value I showed before. So basically, even in industrial scale, like this price is possible. Another very famous organic electrosynthesis process is the toluene oxidation, as shown here. And in that process, the toluene derivative, the starting material, is oxidized by 4 electrons to afford something called acetal as an intermediate, which is equivalent to the aldehyde. And this process is successfully industrialized by BASF in Germany. And they are using very unique cell configuration as shown here, which is called capillary gap cell. So in this cell, there are 2 driving electrodes, and bipolar electrodes are basically making a pile. And it's a cylinder pile, and the electrolyte go into the inside, and the solution comes from the capillary gap, so like a 1 or 2 millimeter capillary gap from the inside to the outside. So this is very successful, famous textbook, organic electrochemical process, and they even developed the reaction for paired electrolysis. Paired electrolysis is the idea to use both sides of the electrode to make desired product. So in a perfect world, it realized like 200% of the Faraday efficiency. At the anode, the acetal is formed, as I mentioned before, and at the cathode, the diester is reduced to give a benzolactone derivative. So here's a brief summary, a brief history of the organic electrosynthesis. So of course, the dawn, so the beginning of the electrochemistry is back in 1800 by the invention of voltaic pile by Volta, of course from Italy. And yeah, at that point, electrochemistry basically started. And very interestingly, the history of organic chemistry starts a bit later. So 1828, the first urea synthesis was reported, and that is like known as the first organic synthetic reaction. A bit later, the Faraday reported the electrolysis of acetic acid, but he could not determine what he was making in that reaction. A bit later, Kolbe identified that the electrolysis of acetic acid affords the ethane. So now that reaction is known as the Kolbe electrolysis, which is one oldest legendary reaction, organic electrosynthetic reaction. 100 years later, almost 100 years later, so middle of the 20th century, the Simon process is industrialized, which is an industrial electrochemical fluorination process. And Monsanto process and BASF paired electrolysis are also reported and industrialized. One thing I want to emphasize here is that there's one contribution from very important contribution from Japanese company Otsuka, so Otsuka menthol process. Although this, unfortunately, this process is not like continued anymore. But the important thing is that Otsuka realized the first industrial electrosynthetic process using organic solvent. So, it's going too far, but after that, there's a time people worked more on the thermochemistry, but after the Paris Agreement, 2015, more and more companies are making effort to decarbonize, so reducing the CO2 emission from their process. And that's why more and more people are interested in the electrosynthetic process. And now I want to say that this period as a renaissance of the organic electrosynthesis, and I'm happy to use this word in this place, Italian pavilion. Okay. We are not the only people saying this. So the electrification of organic chemistry is a world trend, I would say. So you can take a look into these articles, such as like Chemical and Engineering News, Chemistry World, and MIT News. All of them are discussing about the possibility of using electrochemistry for organic synthesis. And also in academia, more and more people are starting using the electrochemistry for the sustainable organic chemical production. And actually, there are some large funding starting in European Union and the US. So in European Union, from this year, Horizon Europe are decided to fund the project called Electrify It, which is a 2.45 million euro funding. And also in US, NSF funded Center for Synthetic Organic Electrochemistry which actually started from 2018, but this year they continued to, they decided to extend the time period for 5 years, which is like 1.98 million US dollar. Also in Japan, although they're a bit smaller, but there are several projects are ongoing for the electrosynthesis. A unique feature, one thing I want to emphasize is that like in the funding in EU and US, these are organic electrosynthesis oriented. It's not about the hydrogen production. It's not about the CO2 reduction. So these all are focused on the organic electrosynthesis, which have never happened before, I think, in a larger funding scale. But now it is happening in academia worldwide. So let's switch the gear, and I'd like to introduce our own contribution to the field. When we talk with the industrial people that let's electrify their process, they say, okay, electrosynthesis sounds very interesting, but this could be a problem for their real-world production. One is the limited surface area because in thermochemistry, the reaction happens in a three-dimensional space, but in electrochemistry, the electrode limit the reaction kinetics. And also, the solution resistance could be a problem because we're using organic solvent, which have a relatively lower dielectric constant, which means that which tend to generate resistance, so which means the energy loss for the process. And another problem is the use of the supporting electrolyte. Although we are using, we can use the electron directly to the reaction, but we need a supporting electrolyte for the reaction, which increases the cost for the process. So these three needs to be addressed at once, and we are thinking, okay, is there any methodology to do that? And the answer is the use of the solid polymer electrolyte, SP electrolyzer, which also introduced in the previous Hayashida-san's presentation. And in this solid SP electrolyzer, we are using the thin membrane, SPE membrane, and sandwich the membrane with the electrode. And the electrode is three-dimensional, so it really has a really large surface area, ensure the fast reaction kinetics. And also, thanks to the zero-gap electrode configuration, we don't really need to add any supporting electrolyte. And the energy efficiency could be very high. And because we don't need to add any supporting electrolyte in solution, non-polar solvent like benzene or hexane toluene could be used for the electrolysis, which is not possible for conventional electrolysis process. We are not the first people invented this system. This is, of course, used in the fuel cell and water splitting. And also importantly, I have to mention that Japanese energy company, ENEOS, has now building a pilot scale for the hydrogenation of toluene to methyl cyclohexane for the hydrogen carrier purpose, which is also the organic electrosynthesis, I would say. And here we can see, of course, in this project, Nora and ENEOS had a very fruitful collaboration to enable their scaling. And we are taking this technology to make a more value-added variety of chemicals to realize the sustainable chemical industry. So SP electrolysis system could be classified based on the type of the membrane. So PEM, proton exchange membrane, and AEM, anion exchange membrane. I'm going to introduce both of the system, but PEM has an advantage of the high proton conductivity, low cell voltage. but the problem is that the catalyst is limited to the precious metals. On the other hand, AEM is under development, so the resistance could be a bit higher, although because of the basic environment, we can use the base metals, so very cheap metals, for the electrolysis. So there are always pros and cons, and I'm going to introduce some examples. Oh, yeah, before that, I have a movie for the electrolysis system. So the system as shown here, there's a membrane, anode, and cathode. And at the electrode, we have a catalyst, ionomer, and by running the electrolysis, so in this case, it's a PEM electrolyzer, proton moves through the membrane, and the electron travels the outside circuit. On the other hand, in the case of AEM, an ion such as hydroxide ion moves through the membrane. And at the cathode, surface hydrogen species is generated, and which is used for the reactions such as hydrogenation reaction. So we have already reported several industrially important reactions using the SPE system, and the important thing is that all of these reactions are done under ambient pressure and temperature. So one example is the hydrogenation of cyclic ketone to form the cyclic alcohol. And the important thing is that we could run this reaction so diastereoselective manner. So we want the this configuration, so which is called cis, because this is a fragrance intermediate, and the cis isomer is better for that purpose. And yeah, we could do the reaction with the PEM system, and yeah, we could run the reaction even at the gram scale. So it's a bit larger scale for the organic synthesis. And we have also reported the hydrogenation of pyridine to piperidine. In this study, the reason why we chose this reaction is that the skeleton of shown as red, so that is called piperidine, that is very important skeleton for the pharma industry. And after the optimization, we could run the reaction very efficiently. So until the 5 farad per mole of the electrolysis, almost quantitative for the efficiency. And after passing a bit excessive amount of electron, then we could obtain the desired product in a quantitative yield. And the system maintains the capability even after running over 300 hours. And the examples I showed here, I showed before the reduction, so cathodic reaction, but we are also working on the oxidation chemistry as well. When we develop oxidation chemistry, one thing we are thinking is that new oxidation reaction could replace the oxygen evolution reaction in hydrogen evolution process. So we all know that we want hydrogen from the sustainable energy, and by electrolyzing the water using the sustainable energy, we can make a hydrogen gas. On the other hand, we have to make oxygen at the anode, but there's no value for anode, and which is also energy consuming. So if we could replace the OER to other easier oxidation reaction, then we can reduce the energy required for the reaction, and also we can actually make a valuable chemical for the anodic side. So we can basically reduce the cost of the hydrogen. So that's the idea. And one example is the oxidation of the benzylic alcohol. So if you think about some dynamics of the reaction, water electrolysis requires 1.23 volt at minimum, but for the oxidation of benzylic alcohol for the anodic oxidation reaction, then the net reaction only requires 0.38 volt. So much smaller energy required for the hydrogen evolution as well as the anodic production of the desired product. And I'm not going to go too much detail about this, but we realized the oxidation of benzylic alcohol to benzoic acid, benzylic alcohol to benzaldehyde using an ion exchange membrane system, and we successfully used the several base metal catalysts for this reaction. To wrap up, so in today's presentation, I hope I could convince you guys so why the electrosynthesis is very interesting. So electrochemistry, electrosynthesis could give some solution to decarbonize the industry and a circular economy, as well as its innovation platform. And the last message from me is that the time is now, and let's electrify the chemistry. Last not least, I'd like to thank all the members in the group. I've done no experiment of this work. So student done all these experiments. And also, I want to thank to Atobe Sensei, he's there. And we are running the lab together, and he's always very supportive, and we are developing the technology together, and we are taking very exciting, enjoyable journey. And with that, I'd like to finish my talk. Thank you, everyone, for kind attention, and I'm happy to take any of your questions that you might have. Grazie.
Yes, thank you very much. So any questions, comments from the audience? Nama, please.
Thank you for the nice presentation. So my question for you is, so when you work with these organic electrolytes, so when you use this AEM or PEM-like membrane, so when you do the synthesis, do you see any degradation on these membranes? Because sometimes what we know, these chemicals can be very harsh for the membrane.
Surprisingly, so after optimization, not really. So we don't really see significant degradation. But for example, you need to be very careful about like which membrane you use. So for example, I think like most of the anion exchange membrane is made for the water or CO2 reduction purpose, and which is not tolerant to the organic solvent at all. So like if you put the AEM in the organic solvent, it's gone. So you need to be very careful. You need to be very careful which membrane you choose.
Thank you.
Any other questions? Mike, please.
Thank you for your nice presentation. I learned from a lot.
Thank you.
In the slide of BASF paired electrolysis, in that slide, you showed two different products in one pot. So how to separate that chemicals into pure two electrodes, or how to purify that product?
Yeah, thank you very much. I believe that reaction is also done in the capillary gap cell invented by BASF. So that is basically a undivided cell configuration. So there's no way to separate these two materials during the electrolysis. So in that case, there's a need for the downstream treatment. And I think it's a very nice point to because a downstream treatment requires sometimes a lot of energy and could cause a large amount of CO2 emission. So yeah, in that case, they are separate. I believe they are separating the products at the downstream. But for example, it may be possible to use by using the divided cell configuration. Now people don't really need to separate things. Thank you.
Okay, so then thanks. Let's thanks again to Shida Sensei. Okay, so then the next presentation before our coffee break is from Dr. Namal Waninayake. Okay, please.
Hello, everyone. First, I would like to thank the organizers. And this is my first time in Japan, so I'm very excited to be here. So let's just begin. So today, in my presentation, I'll be discussing what's beyond hydrogen for Nora and Nora's electrochemical innovation for energy transition. So this is the outline of my presentation. And before we dive in, I want to quickly introduce Nora Tech. So we are located in state of Ohio in the United States. So in the city of Cleveland, it's next to Lake Erie. So we have so many attractions. So if you ever visit the area, these are the things you don't want to miss. So our office is located at Discovery Lane, where we have our R&D laboratories and administration and technical support and sales group at Nora Tech. And in about 15 minutes from our office, we have Nora Tech Manufacturing, where we manufacture mixed metal oxide electrodes. And also we have newly built Innovation Center. It's capable of scaling up production of gas diffusion electrode and also nickel-type anodes for alkaline water electrolysis. So this is our USA Nora R&D group structure. So we have a team doing water electrolysis, mainly focusing on hydrogen, AEM, and PEM systems. And we have electrode technology, focusing on ET markets and energy transition programs. And we have a cell and pilot test lab engineering group. They support R&D groups by designing test stands. And also today, my main focus is on new application research that we focus on applications beyond hydrogen. So for today's talk, I'm going to discuss a couple of projects that we've been doing for the past few years. So you can see here, most of these projects funded through US Department of Energy, which is kind of similar to NEDO in Japan. So during this presentation, I'll be going through all these highlighted projects. So other than these projects, we also have internal projects, carbon conversion projects that we are conducting right now. Okay. So the first project I'm going to discuss is called electrochemical conversion of carbon dioxide to fomate or formic acid. This project, as I mentioned, funded through DOE and through the ARPA-E program. So the main motivation for this project is to reduce CO2 generation from the fermentation systems. So if you take a fermentation reactor, so it releases a lot of CO2 during the fermentation. So our main goal was to take this CO2 and put it back into the electrochemical reactor and then convert this carbon dioxide to fomate and then feed it back to the fermentation reactor such that we can improve the yields of the final product. Those are lipids, which can be used as a precursor for jet fuel. To do this project, we have other partners. First partner is Genomatica, whose expertise in fermentation. And we have National Renewable Energy Lab, who help us with the cell diagnostics. And University of Oregon is helping us with the bipolar membrane component in this electrochemical cell. And as Nora, we bring in our electrode, and we did the electrode scale-up testing as well as cell design. So now let's look at quickly how this cell operates. So starting from the anode side, we have anolyte, typically 1 molar KOH solution. And next to that, we have a DSA anode. And after that, what you have something called bipolar membrane. So if you are not very familiar to bipolar membrane, the best way to visualize it it's a lamination between cation exchange membrane and an anion exchange membrane. So under electric field, when the water gets into this junction, what's going to happen? It's going to dissociate water, and this dissociated water will be protons and hydroxyl ions. So the protons will be pumped into the catholyte channel, and the hydroxyl ions will be pumped into the anolyte channel. So then we have this finite gap, which contains the catholyte, typically like potassium bicarbonate solution. And then we have a De Nora gas diffusion electrode with a catalyst, where we feed carbon dioxide, and then this catalyst converts the CO2 to formate. And this formate can combine with protons and then resulting formic acid. So these are the main parameters we investigated in this project. So I want to mention 80% of the effort was put into developing the gas diffusion electrode component and also for electrochemical testing. So here we studied the effect of a GDL type, that means gas diffusion layer, and the catalyst and the electrolyte effect on the selectivity towards formate. So let me focus on the catalyst and electrolyte first. So we screened tin dioxide and bismuth oxide as the catalyst candidate, and also potassium sulfate, that is unbuffered electrolyte solution, and also potassium bicarbonate, this is a buffered electrolyte solution. So what we realized when we combined bismuth oxide and potassium bicarbonate electrolyte, we started noticing high formate Faraday efficiency. So we down-selected these two. And all the results you're going to see in the upcoming slides were obtained using 25 square centimeter electrochemical cell hardware, and then later we scaled it up to 250 square centimeter cell size. Yeah, now let's dive into our GDE design. So there are two sets of gas diffusion layers I'm comparing here. So what you see on the top is maybe familiar to some of you, called the Sigrid 39BC. This is a commercial fuel cell type gas diffusion layer. When you look at the cross-section of this gas diffusion layer, what you see is a very open pore structure, which can result in low hydrostatic head. That means if you have a water column next to the MPL side of the gas diffusion layer, the water can slowly penetrate into the gas channel. So what you see on the bottom is De Nora gas diffusion layer. We call it chloralkali ODC-like design. So here you can see we have a tight pore structure, which can also result in the high hydrostatic head. So that means if you have a water column, this electrode can manage the water column very well compared to this one. So it will be obvious when we look at the results. So the way to read these results, the y-axis shows the Faraday efficiency, and the x-axis shows the current density. What you see in the orange color is the formate Faraday efficiency. So clearly, when we use our De Nora GDL, we notice we can push the current density to higher values while maintaining high Faraday efficiency for formate. So we believe this is coming from the higher flood resistance resulting from our De Nora gas diffusion electrode. So we also did some process optimizations and collect data for long duration. What you see here is the formate selectivity versus the time we tested this system. So our project target was to maintain 70% Faraday efficiency for formate, but you can see we ran it over 200 hours at this current density. And by doing process optimization, we also able to make about 28% formate solution. And during this process, we also was able to demonstrate our carbon dioxide single pass efficiency can be exceeded to about more than 50%. So this slide basically summarizes everything I just discussed. So I'm going to move to the next phase of this project. So here, as I mentioned, now we scaled up the same electrode components to 250 square centimeter size. So this is the electrode, the back side of the electrode, and this is the front side of the electrode, where we have a catalyst layer, which is bismuth oxide. So we deposit this catalyst layer using a slot die method, so which can result in very uniform coating. So what you see here is the part of the long-term test results. And after 14 hours, we also hose down the backside of the gas diffusion electrode. There is actually a video. It's not playing for some reason. But when we hose down the backside of the electrode, we can see water is bouncing off. That means it's maintaining good hydrophobicity. So also we noticed there is no major degradation of the catalyst or any other component of the system. So this is the summary of what I just discussed. So this is the 250 square centimeter cell that we designed for this project. The other thing to highlight here is that when we scale up, we notice our single pass efficiency can get close to 50%, but not exactly. So we came close to like 46%. So with that, I would like to wrap up this part of the presentation. So to summarize, so we optimized the GD structure to obtain higher selectivity for formate, and we down selected the catalyst and electrolyte chemistry to enhance the durability. Also, we demonstrated the scalability of the electrochemical system. However, there are two main things I want to highlight. To achieve the commercialization, we realized we need to make major improvements in the other components, such as bipolar membrane. As an example, so what you see on the bottom is the paper published by National Renewable Energy Lab, where they break down the cell voltage. So you can see here, the bipolar membrane-related components take up to about 50% of the cell voltage. So this is a huge space we should work on to minimize. And the other issue is the downstream product purification can be very expensive. So as you can see from this techno-economic analysis paper, so formic acid separation cost can add significant cost to the final product. So therefore, if you're making potassium formate versus formic acid, it makes a huge difference. So therefore, it's very important for us to design the system such that we have to minimize the downstream separation. With that, I'm going to shift gears and move to the next project. This is we call COTA. That means electrochemical CO, carbon monoxide conversion to high purity acetate. For this project, we have other partners. Rice University is the lead of this project. And we are bringing our electrodes and also electrochemical cells for this project. And National Renewable Energy Lab, again, helping us with diagnostics and transport analysis. And Kraton is a company who makes anion exchange membrane. And University of Wisconsin-Madison is doing techno-economic analysis. So as I mentioned, the goal of this project is to make high purity acetic acid. So acetic acid is a very important chemical precursor in industry. So as I mentioned in the previous project, one of the main challenges in this in the electrochemical production of acetic acid is that typically the product is contaminated with guest ions such as potassium, sodium, bicarbonate or hydroxyl ions. So therefore, what we need to do, we need to engineer the system such that we can minimize this ion contamination. So as a result, we came up with this cell configuration. So what you see, starting from the anode side, it's very similar to PEM water electrolyzer. We have an anode with the precious metal catalyst, then we have a cation exchange membrane, and then what we have something called the porous solid electrolyte layer. So next to the porous solid electrolyte layer, we have anion exchange membrane, and then we have a de Nora gas diffusion electrode with a catalyst which can convert carbon monoxide to acetate. So then this acetate is going to cross the anion exchange membrane. It's going to come into this solid electrolyte layer. Protons going to come from the anode side, and they combine. And now then you can use deionized water or humidified gas flow to pull the high purity acetic acid. So these are the overall technical targets for this project. So one of the things to highlight here is that we have very ambitious goals to achieve greater than 70% acetic acid Faraday efficiency at greater than 300 milliamps per square centimeter current density. And let's now look at what are the design basics for the anode. So we were fortunate enough, so we also had a previous PEM water electrolysis project, which is also DOE funded project, where our team developed this anode PTL. You can see the structure of this anode PTL, which also contains a small like microporous layer, which help us to deposit very small amount of catalyst while maintaining high performance. So the other thing we did, we also applied some protective layer, in this case platinization, to prevent the anode oxidation. For this project, what we did, starting with this substrate, then we deposit this DSA like ink, and then this non-noble metal containing ink was applied and then subject to thermal curing to make this DSA electrode. On the next slide, I'm comparing the performance of our DSA thermal cured electrode with some commercial iridium oxide anode. So here you can see the voltage decay over 1100 hours for our electrode is about 2.5 microvolt per hour. However, these commercial iridium oxide anodes from dioxide material resulted in high voltage decay. So we believe this high decay rate coming from the oxidation of the carbon substrate. So this is the cathode side. Initially what we did, we prepared copper-based gas diffusion electrode by depositing these copper nanoparticles on our gas diffusion layer because copper is a good catalyst that can convert carbon monoxide or carbon dioxide into these multi-carbon products. So we prepare this electrode using, again, our lab-scale slot die coater, and also note that we have the capability in the future to make this fabricate this electrode in larger scale in our innovation center using this roll-to-roll coater. So before I show you some technical slide, I want to show you how the cell is being put together. This is, for example, 10 square centimeter cell assembly. Starting from the anode, then we put the Nafion-like cation exchange membrane, and then here's the solid electrolyte layer. So in the catholyte channel, and the catholyte is going to enter through this channel and go through it, and then comes out at this end. And then we put the anion exchange membrane, and then we put the gas diffusion electrode and tighten the cell with these PTFE gaskets. So these are some results we obtained using commercial copper nanoparticles. So the way to read this plot, the y-axis shows the Faraday efficiency, and the x-axis shows the current density. And this data were collected at 400 milliamp per square centimeter current density. And on the top, you can see the hours online. So clearly, when we use commercial copper nanoparticles, we see acetate, which is shown in orange color, and the green color shows the ethylene, and gray color shows the hydrogen Faraday efficiency. Clearly, when we modify these copper nanoparticles, that by means what our partners do, they dope copper with elements like palladium or silver to improve the selectivity of acetate. So as you can see, when we use these modified copper nanoparticles, we can increase the Faraday efficiency for acetate, and that means it's a decrease in the ethylene Faraday efficiency while maintaining the Faraday efficiency for hydrogen. So our goal in the next step is to further engineer the catalyst such that we can further increase the selectivity for acetate. To quickly summarize this project, so we designed a durable anode that is suitable for this project, and also we have shown the modified copper nanoparticles increase the selectivity towards acetate, and currently what we are doing, we are trying to scale up the system using a 100 square centimeter electrochemical cell. and also our partners working on obtaining comparative techno-economic analysis versus the conventional process. So the last thing I want to mention, even though the solid electrolyte mitigates the ion contamination, there are other challenges in this system. For example, when you use copper-type catalyst, it also generates some ethanol, which can be very harsh on the anion exchange membrane. So it significantly reduces the stability of the membrane. So there are a lot of design principles that we need to use designing these components to keep running the cell for longer duration. So with that, I'm going to shift gears to a different project. This is an upcoming project, so I will show you the way we plan to do it, which is called the decarbonizing the cement and concrete. So as you know, this cement production is responsible for 8% of the global CO2 emissions. Typically, it requires temperature above 1400 degrees C to convert this calcium carbonate to calcium oxide. Therefore, and also you can see at this process, we are releasing a lot of CO2. So our goal is to eliminate this step, the heating step, and replace it with the electrochemical process. For that, we put this team together, the University of California, Irvine, who's leading this effort, and Nora is supplying electrodes and electrochemical cells that I showed you in the previous project. And Oak Ridge National Lab is doing making mineralized concrete, and we also have a potential off-taker of this cement called the Argos cement. So the main concept in this project, so if you look at this figure and envision the electrochemical cell that I showed in the previous project, it's kind of similar architecture. So what we are planning on doing here, so we're starting with the calcium carbonate. We can put it in some kind of acidic environment on the anode side of this reactor. And through the proton exchange membrane, then we can pull the calcium into the middle compartment. And from the cathode side, we can obtain hydroxyl ions and precipitate this calcium hydroxide. Then we can heat up this calcium hydroxide and convert it to calcium oxide, which only need to heat it up to like 400 degrees C. So when we do this reaction, precipitation, we can run this reactor on the anode side. It can be oxygen evolution and hydrogen evolution here, or alternatively, we can also consider doing CO2 conversion on the cathode side. So moving forward, what we also planning on doing on this project is to design like 500 square centimeters size cell stack, which can be used to generate about 70 kilograms of cement per week. And also, we have a commercial Cyclo product from Nora, and we also want to evaluate the use of this product to see if we can generate about 450 kilograms of cement per week. And also, in this project, we will also be exploring the component stability, of course, and also the achieving comparative techno-economic analysis versus the conventional cement making process. To finally conclude my presentation, so as you can see, Nora do see a foreseeable future where the electrochemistry plays a significant role, shifting towards sustainability. And we also recognize that beyond hydrogen, we do see opportunities in other fields like carbon conversion, and also recovery of essential raw material and metal to strengthen the supply chains. For example, the cement decarbonization project, if you can envision, instead of calcium, you can also have other elements like lithium. And to achieve those things, we think most effective way to do this by fostering more partnership among academic institutions and industrial players, as well as national laboratories. With that, I would like to conclude my presentation. I am
happy to take any questions. Thank you.
Okay, Namo, thank you very much. Any questions, comment from audience? Shio-sensei, please.
Thank you very much for the very nice talk. I have a question about the second topic. So, so you mentioned to make the very pure acetic acid, you guys designed the basically bipolar configuration with a medium porous layer. So
Yes, yes.
why, for example, something like a simple AM configuration cannot do that type of pure acetic acid
Right.
production?
Right, good question. So I think the issue is that when you use normal AEM, so acetic acid is a liquid product. So it's going to go through the AEM, and then it's go to the anode side, it gets oxidized very easily. So it will no longer be acetic acid. So the other issue is that, again, the contamination. So in that case, if you use, of course, if you use water, maybe you can make acetate, but at that point, you will be probably doing acetic acid, like further oxidation.
So basically, like suppressing the crossover, I think.
Exactly.
So what is a role of the medium layer? So
Oh, the
can you-
thickness?
Yeah. So then, I mean the role. So what does the medium layer do?
Oh, what does the role?
Yeah,
It's
yeah.
maintain the ionic conductivity without having an actual electrolyte.
Okay, very
Because we are not, otherwise you have to feed like potassium bicarbonate or potassium hydroxide like solution, right?
Okay.
So with this solid electrolyte layer maintains the ionic conductivity in the electrochemical cell.
Thank you.
Any other comment, questions? Okay, so the plan is to have a coffee break from now. I guess Italy is going to bring in the coffee now. So, and we will start the next session from 5 minutes before 4 p.m. So please have a coffee and break. So like I said, the bathroom is outside of that door. So please use. Okay, so thank you very much. Let's go to the break.